Alright guys, so we're gonna get started now. There might still be people that trickle in. Otherwise, it might look like you guys get extra seconds. So that's cool.
Hey, it works. Okay, great.
So,
Welcome back to lecture 7.
last one of this quarter. 3 more after this. So, it's gonna be hype. Alright. Constructively closer to the little guy.
Yes.
Alright, so this is a reminder that actually now we're starting on project 5. That's distance. Oh, actually, wait. I don't know. Oh, sorry, I'm reading this wrong. Alright, so project 5 is going to be launched tonight. Right after this lecture, we're going to talk about game Guido a little bit too. We'll probably go through the spec again because you guys liked that last time. Distance sensor and CS2 midterm, I guess, got GG. So I hope you guys did well on that. I know a lot of us we got a lot of extension requests because of that. So I really hope you did well because of it. It's fine. We don't care if you guys for an extension. We just want to make sure that you don't suffer. Game Guido, this is a lot more CS heavy. It's the most CS heavy project. It's going to be minimal wiring, but a lot of coding. It's going to be released today. I said that already. You're going to have a while to do it. So we'll get more into the heavy details after lecture. And then also, we're going to have a game Guido competition. This is big. We have Operation Ice Spice underway. We're trying to work that out. You guys don't know what that is. I don't know what that is. Also, that's going to be week 1 when we're back. It's going to have prizes too. Like we're actually using, because we have a lot of production over the a budget, so we're going to use some of it for some cool prizes. And then also, just it's a chance to be creative. If you guys have like a little bit of an knack for CS Project, if you really like CS Project 3, it's nothing like that because Arduino only has 2 kilobytes of storage. So obviously, you can't like of RAM on board RAM. You can't really like do something as hefty as that. You can definitely do something that's a little bit easier than that. So, again, we'll get into that at the end of the lecture, and then Miriam's going to take it away.
Okay, yeah. So there is one more. Hang on. That's right. Yes, very special event reminder. So tomorrow we're going to have IEEE officer speed dating. So if any of you guys or anybody who's watching the recording, like tonight for whatever reason, is interested in being the next ops lead, you should definitely come out to see us at speed dating tomorrow. Or if you're interested in any other IEEE officer position, definitely just show up and like say hi to whoever the current officer is. You can get more information about specific positions. Show your interest in being in the board and being an officer, and yeah, just like come and hang out with us and have some free food because they also have free food there. Also, just know that if you can't make it, but you are interested in a particular position, we recommend that you just like message the person so that they are aware that you're interested and that they can give you more information that will make you make it easier for you to craft your application to be successful.
Us?
We? Oh.
I don't know if we should answer that.
I mean,
I mean,
off the recording. Maybe we will.
yeah.
Off the record.
In terms of, and it's not actually fake, but just talk to us. If you guys can't make it tomorrow, it's totally fine. Just if you're interested in being an officer, just DM us anytime. Probably both together so that we both know what's up. But we're down to talk to you about it if you're interested in the role. We're interested in any role, get a lot of connections. Too afraid to like talk to maybe some people that I'd recommend you talk to them first. But if you're too afraid and you want to get like a foot in the door first, we could talk to them and reference you and say, hey, like they want to set up a meeting, get on their Discord handle or something. So just like keep it open mind. You don't have to be an officer if you don't want to be. Obviously, it's a great role. I really enjoy it. I love talking to you guys and doing these lectures. And Miriam does definitely too. So just check it out. Check out the dating profile too. Well,
Yes, IEEE data match. Okay. All right, that's all the announcements. So now we can get into the actual lecture. So for a change, I'm actually going to be going first, and I'm going to be talking about communication protocols. And then we're also going to talk a little bit about some CS stuff, arrays and functions, and then we'll get into the project. But first things first, communication protocols. So I know there's like a lot of letters and a lot of words on the screen that might be like kind of intimidating. So I didn't like fit in the slide for this. So I just kind of want to preface this whole section by saying that like these things, although they seem kind of weird and arbitrary and like very highly technical, they're actually super, super important. And if you can grasp these sort of communication protocol topics, it'll be very helpful for you in the future if you are to like pursue like using microcontrollers and like things of that nature. And the reason why is I can give you like a more concrete example. For me, if you are like competing in idea hacks, for example, essentially the way those things works is when you develop something from the ground up, you have some kind of central microcontroller, and then you're using that central microcontroller to control all these different like peripheral things. Because you're just like, if you just have an Arduino by itself, that's not really going to do that much unless you're like a CS person, of course. But we are not. We are hardware people, so we're like actually creating things, with components and stuff. So in our case, to be able to use all these different peripherals, you're going to need to be able to communicate with them using these types of communication protocols. And if you have a deep understanding of what each communication protocol is and how to implement them very easily, then it'll be easy for you to just like from the ground up make something really cool out of basically nothing. I don't know if any of you went to Idea Hacks. I think I saw a few of you there. My Idea Hacks project, which was a finalist, was literally just like 3 Arduinos hooked up together and connected to like a bunch of random peripherals. And we were a finalist. So like, if that doesn't like, give you some kind of incentive for like paying attention to this lecture, I don't know what will. But so yeah, even though they might seem really difficult right now, I promise you that they are actually really important and they are actually like very highly useful in industry. And yeah. So now I'll actually get into what these things are. Okay, so communication protocols. So if we have a microcontroller and we want to control some other component that we have, we need to have a way to talk to it. And, there could be, if we didn't have it standardized, we could have, one person, it's kind of like different languages. You're trying to speak to this person in a certain language, and they don't understand that language, so that you won't be able to talk to them at all. So instead of, dealing with all that, we have these things called communication protocols, which are just a standard way of sending signals to different peripherals so that you can very easily talk with them. And because it's standardized, you can just like look up some kind of data sheet, and then you'll be able to very easily control that peripheral using your microcontroller. So before we get into the nitty gritty, I have a couple of definitions here just so that some things down the line make a little bit more sense. Starting off with a clock signal. Clock signals are important because you want your microcontroller and your peripheral to be kind of like on the same, on the same wavelength. That sounds kind of dumb. Essentially, you need it to be like ticking in the same time because the signal is going to oscillate between high and low, and corresponding to each of those high and low signals is when your peripheral is going to be sampling the data that is coming from your microcontroller. Because we're only going through like one line, and one line can only go high and low. So if you can't like send a whole bunch of information that way, so you need to be able to sample when it is high and when it is a low, kind of like talking binary, and that's what we use our clock signal for. Okay, so asynchronous is a type of serial communication that does not use a clock signal, while synchronous is one that does use a clock signal. We'll talk about more why asynchronous things can still work very shortly. Another couple of interesting things are baud rate. Baud rate is mostly important for UART, but that is the rate essentially at which information is being sent out or received. And then finally, bandwidth is going to be your maximum data rate. And here are just a couple of examples of asynchronous and synchronous. So asynchronous at the top, that's an example of like UART communication. So, I don't want to talk too much about it right now, but that's basically how it would look like. Whereas synchronous, you can see the data is kind of like synced up with the clock signal. So you have 2 of those lines going at the same time. Okay, that's just kind of like a brief overview of some of the important definitions. But it'll maybe make a little bit more sense once we get into some actual protocols. Okay, so there are 2 types of communication mainly, that is serial and parallel. You don't really worry a whole lot about parallel. It's just, good to know. Serial is when data is sent one at a time, and it's going to be slower than parallel, but it is less likely to be corrupted because it's only one line. and it's also better for long distance. Whereas in parallel, all data is being sent at the same time, as you can see, like through a bunch of different pins, and that's the reason why it is faster, but also more easily corrupted because there's more like points where it could get corrupted, and that in general is better for short distance as opposed to long distance. So you can also see a couple of examples of some popular like communication protocols. So we have like things that we're going to be talking about, I2C, SPI, USB, which is a type of UART, and then these are a bunch of parallel ones, which you also might see if you were to like rip open something and look at all the connections in there. You would probably see some connections like that. Yes?
What is CAN? Is that not
It might be these. I don't know. I don't know it personally. I guess I'd have to look it up. But have you like used it before, or?
Yeah, and I was asking someone like the difference between that and I2C, and like why would you choose one over the other? And I was wondering if it's like that.
Okay. Yeah, I'm not personally familiar with it. I know that I squared C. Well, this is another thing that we'll kind of get into more later. But I squared C is generally like more popular because it's like a more well-known name. So if more things are compatible with I squared C, then you're going to want to use I squared C just so that you can like hook it up to more stuff. But okay. All right, that's serial and parallel. So for the most part, I should say before I went to the next slide, for the most part, we're going to be just talking about serial. We don't really talk about parallel, at least in this lecture, although parallel is also important, especially because it's fast. Okay, but starting off, we have UART. So UART is actually something that we use very frequently because UART is the way that our serial monitor works. If you recall, we have to do this thing called serial.begin 9600, and we said that was the baud rate, and we kind of like glossed over that way back when we were talking about it. But now we can actually get more into what that serial stuff is actually doing. So essentially, brief overview of how UART works. UART has one master and one slave. So basically one microcontroller, one peripheral. We can't add more peripherals or more masters. That's just, it's one-to-one. And it's an asynchronous type of communication. The reason why asynchronous still works is because we have that baud rate. That baud rate essentially takes the place of a clock signal. So both the master and the slave know kind of like what the time scaling is. When do I need to sample each of the bits? Yeah, this is what I said. Instead of a clock signal, we're also going to have to add a start, stop, and parity bit. That way we know when the signal is being sent, when the signal is stopped being sent, and the parity bit is used to, I believe, make sure that there isn't any data corruption. The parity bit has something to do with like adding the bits together and making sure like there's some kind of total sum that adds up to this thing. Anyway, that's what the parity bit means. Sometimes there is a parity bit, sometimes there isn't, but that's another component of it. Parity bits are added to the location of the data bus. I guess that's also true, but yeah, okay, anyway. So the physical wiring, usually it's just going to be the RX and the TX pins. So essentially you have two wires. RX is receiving, TX is transmitting. So the RX on one side is going to go to the TX on the other, and then the TX, or the RX on the other side is going to go to the TX of the other one. And then of course they have a mutual ground because that's kind of like normal. Okay, that's like an overview of UART. Does anybody have any questions on like UART just in general? Okay. I'll just talk briefly about how like your serial monitor kind of works in this regard. So this is with the serial monitor. As you know, we did like the serial.begin 9600. So that's essentially setting the baud rate of your serial monitor and the baud rate that for which your Arduino is communicating with it. So I know some people had some like issues with like when they tried to use the 1 and 2 pins on their Arduino while their Arduino was being programmed. I don't know if you've noticed, your Arduino is plugged into your computer via USB, and like I mentioned, USB is a UART protocol, and pins 1 and 2 on your Arduino just happen to be the UART pins. So the reason why if you have something connected to those pins while your Arduino is being programmed, the program gets kind of like corrupted, and then the upload will fail. So that's the reason why you can't have anything connected to your 1 and 2 pins on your UART, because those are the TX and RX pins. Serial monitor also uses the UART, and like I mentioned, because it is one-to-one, so you can't have like you can't use the serial monitor with your Arduino while having another UART thing connected to your Arduino, because that is like the master and the slave connected to each other. It's only one-to-one. You can't have more connections than just one. Okay. Cool. So now we'll kind of get into like a snapshot of what UART would actually look like. So UART will begin with the master, which is the transmitter, going through the TX pin. So it will receive data from a data bus, just like in general, and then itself will add a stop, start, and a parity bit if necessary. And then at the TX pin, it's going to send the data out at the respective baud rate that it's been set to. So then this is kind of like how it would look like as the data is being sent out from the TX pin to the RX pin on the slave. So the slave then will sample the data at that RX pin from the start bit to the stop bit, and then at the baud rate. So this is the reason why the baud rate is important, because if you have two different things at two different baud rates and it's not going to be sampling the correct information, it's going to get some random stuff in there, as you can imagine. And then once the slave receives that, it's going to remove the start, the stop, and the parity bits, and then we'll be able to collect that data and send it to the data bus if necessary. Okay. Any questions on UART as a whole? UART is probably like the most simple one just because it's TX to RX, although the wiring does get kind of confusing because you'll forget which one's TX and which one's RX, but worst case, just switch the two and then suddenly it'll work. Okay, great. So now moving up to something a little more complicated. They generally get more complicated as we go. Now we have SPI. So SPI stands for Serial Peripheral Interface. Arduino also has an SPI library because Arduino has a bunch of capabilities. Like I mentioned, all your microcontrollers are probably going to be able to communicate using all these different protocols. That way you can hook up to a bunch of different peripherals if they wanted to. Okay, so the difference between SPI and UART is where UART was one-to-one, SPI has one master and many slaves. So there's still one central thing, but it can go to many different peripherals at the same time. SPI also, in contrary to UART, is a synchronous communication protocol, meaning that the master needs to generate a clock signal as opposed to setting a baud rate. Setting a baud rate can be kind of annoying because, you want it to be more flexible than that. So this way, you just have to hook up a pin, and then that way everything is on the same time scale. So the clock oscillations, when it goes from low to high or high to low, is going to tell the receiver when to sample the data that's being sent out by the master. And in this way, we also remove the need for start and stop bit. So it's not like the internal clock, the baud rate is eternally going up and down. Now we just have when the master starts generating the clock signal, then it knows, okay, I need to start sampling here, and then it'll sample at the clock rate. That's a nice thing about SPI. The not so nice thing about the SPI is the physical wiring. So there's a lot of wires going on here. First we have, probably most importantly, is MOSI and MISO. Those kind of stand for master out, slave in, and master in, slave out. Again, kind of confusing, like TX and RX, because they seem to sound the same. And they're also named different things on different data sheets. Sometimes there's copy and CPO and D in and D out, so even more exciting stuff. We also have the serial clock, which is that clock signal I was talking about. And then finally we have the slave select or chip select or load. Those all mean the same thing. So you're always going to have at least 4 wires going between your master and your slave. Okay. Any questions about SPI so far? Cool. In that case, we will zoom in and see what SPI actually looks like. That is the wrong button. Okay, here you go. Okay, so as you can see, there's a lot more stuff going on here, which is an unfortunate thing about SPI, but it's still pretty useful. So first things first, we have the master, which is the transmitter. So it's going to lower the chip select pin, and the reason why we need that is because, like I mentioned, you're going to have one master and many different slaves. So that chip select pin essentially tells that particular slave, oh, I'm trying to talk to you. So that way the slave knows like what's going on, that it needs to start listening to the master. So once it does that, it will begin that clock pin and start sending out the data at the MOSI pin, master out slave in. Then the slave that's been activated by that chip select pin is going to collect the data at the MOSI pin, or I guess in that case would be the MISO pin on the other side, master and slave out. And then it's going to send back a response. Okay, MOSI pin, master out slave in. So it's going to go into the slave and then send out at the MISO pin, if necessary, at the clock rate, if it needs to respond. And then the transmission is ended when the master lifts the CX pin, the chip select pin, and that way the transmission has ended, and it knows that there's no communication going on. So if we look at like the top right of the screen, we can see kind of like how the wiring would look like if we were to have many different slaves. And this is like where the drawback of SVI kind of comes in, where you can see we need to have a chip select pin for every single peripheral, and that gets kind of annoying pretty quickly because you don't really want to take up so many pins for just some communication. But at least it's still pretty intuitive. Any questions about SPI? Yes. Mutual ground is usually, yeah, I guess it's not put on here because it's usually like kind of a given, but in general, if you're going to be using like different peripherals, like on the same, like within the same voltage range, you're going to need to have them at the same ground. That way, because if it's at a different ground, then it might be like a different ground can mean like a different voltage. So you want to keep them all at the same level. That way, everything stays correctly. I've had issues with that before. Any other questions? All right. In that case, we'll move to the next one, which is I squared C. Oh, wow. So the great thing about I squared C is that the wiring is probably the least complicated because all you have is the SDA and the SCL. But before we get into that. So another great thing about I squared C is that you can have multiple masters and multiple slaves. So now everybody can talk to each other. You don't just need one central thing. And the way that this communication works is because each master and each slave is going to have its own address. So that way you're able to communicate to basically everything very easily. This is also a synchronous communication protocol where there is a clock. So that is important. And finally, physical wiring, like I mentioned, you're just going to have two pins. That is the serial data pin. That's where all the data is coming out of. That's where the master and the slave are going to both receive and send data. And then you also have the serial clock, where the person who is sending the message is going to be activating that clock generated by the master. This is also the communication protocol that we're going to be using in Project 5. Just so you're aware. Okay, pretty brief overview. Luckily, I squared C is the most intuitive at a high level. At a low level, however, it gets kind of crazy. So, don't worry, you don't need to like actually know this by heart or anything. But this is basically what's going on. The reason why we're able to simplify the wiring so much and like have so many masters and slaves at the same time is because there is so much information that's being transmitted through the data. But essentially what is happening is first the master is going to bring SDA to low and the clock also to low. That's basically the start signal. And it brings it to low because normally they're high. And then once that happens, it's going to send out the address. So each slave has its own address. So once the slave, it's going to, all the slaves at the same time are going to be like sampling this data and saying, oh, is this my address? And then once it verifies that it is its address, it'll like eventually activate the later part. So there's also going to be a read-write bit at the end of the address frame, and that is what determines whether the master is reading or writing from the slave. So if it's high, then it would be requesting data, and low, that would be sending data. The ACK-NAC bit, so ACK stands for acknowledge, and NAC stands for not acknowledge. So that's essentially the way that the slave says, oh, yeah, I've gotten the message that you're sending. You can 4C is enough, and like the transmission will stop, or it'll have to restart again. Okay, and then next it'll send the actual data, usually 8 bits or 1 byte. And then finally at the very end there'll be some kind of stop condition where SCL and SDA will switch to high, and then the transmission will finally end. So essentially what's happening is that it sends the address and it says, I want to read or write. And then the slave is like, oh, hey, that's me. Okay, you can read or write. And it'll send the acknowledge. And then it'll go back, the master will come back and say, here's your data. And it'll say, oh, okay, I got that data. And then maybe the master will send more data, and it'll say, okay, I got that data. And then eventually the master will be like, all right, I'm done talking to you. And then that will be over. That's all that happens in those 2 pins. Pretty cool. So as you can see, communication protocols, they can get pretty sophisticated pretty quickly, but it's nice because it just looks like 2 wires, and then all this information is being passed across them. I guess 3 wires if you include the ground, because the ground's important. But yes. Yeah, so kind of like I mentioned at like the very start, so the clock pin is important so that the slave knows like when to sample the data. So that clock is essentially just saying, oh, data's here, data's here, data's here. Any other questions about I2C or any of the other protocols? All right. I'm sorry, this slide's kind of overbearing, but okay, summary slide, just going over everything that we talked about. So we started out with UART. UART was probably the most simple. You just have one master, one slave talking to each other. It is very widely used. USB, like I mentioned, like it's like the third time mentioning it, but USB is UART. So we have a lot of USB stuff. So we know UART is pretty cool because a lot of people use it. However, it also has a lot of drawbacks for being so simple. You do need a baud rate. If you don't have the same baud rate, then you can't communicate. It's only one-to-one communication. You can't have multiple things communicating through UART to each other. Well, multiple meaning more than 2. You also are going to need to add start and stop bits due to it being asynchronous, so that it can inform the other when to start listening and when to stop listening. That's all UART. Then we're going to step up in complexity to SPI. SPI is great compared to UART because we can connect to multiple slaves with only one master. However, there's a lot of drawbacks. For example, we can only talk to one slave at a time. Otherwise, the chip select pin, that process isn't going to work. It also needs more wiring, again, because of chip select. You're going to have limited number of pins on your microcontroller, and you don't want like 8 of them to be, used up by chip selects. And finally, confusing names. That's actually mostly a me complaint. I was like, what are all these names mean? But yeah. Finally, we had I2C. I2C, probably the most preferred, probably the most rigorous and complicated. However, you can have multiple masters and slaves simultaneously. It is also very widely used. You might have heard of it before yourselves, and you're probably going to be using it in the future. However, the message format is pretty complex, and understanding it is a little bit more difficult compared to the other ones, where it's just like you have a clock and you have data. This one has like address, read, write, acknowledge, all that other stuff, makes it more complicated. But the wiring is pretty nice and pretty. Okay. Any questions about communication protocols in general, how you can use them, things like that? Okay, great. In that case, that is all from me.
All right. Well, you guys sure you don't have any questions? No? No? Okay. All right. Feel free to ask questions at the end of the lecture. My section is really, it's gamer time. As you can tell, these slides, Miriam brought it up, these slides are kind of outdated. It's back when Morbius was still trending.
We made them over the summer.
Yeah. So I'm just going to be going over arrays, functions, at GameGuino, and the GameGuino project for you guys. Okay. All right. So, as many of you probably already know, what an array is. All right. So how we declare an array is the item type, the name, and the size of it. Okay. It's a method for storing information, and they save data consecutively. Remember, there's various types of arrays. You can do two-dimensional, three-dimensional. The main type we use is one-dimensional. It's just one set don't, well, at least in C++. So Arduino, like we said before, it's based in C, and kind of by default C++. It's able to process strings and C strings. You have to include the string library, just like you do in C++ with C32 and C31. But other than that, a pointer might be useful for the scope of ops. We're going to recommend like a loop, like a for loop, or a while loop. Some people like the while loop more. I don't understand that, but it's okay. For is pretty good at iterating. So other than that, I think that's pretty self-explanatory. Tori, does anyone have actually any questions on how arrays work, why we use them? No? Think about it, it's like a list. Like we're just trying to sort it out in lists. Actually, Python can call lists too, which is a better name, but it's okay. Alright. So we actually have a few examples of arrays here. Arrays can be characterized by string, double, character, integer, very common. Double, we went over that outside before, but just a reminder, it's like decimal. Integer, it's always going around to the nearest one. And then in terms of us iterating through, we declare a for loop, and then we say the integer. So integer I, there's 4 different sets of data, as you can see in each array, and then we have it print out the player's name, how high they are, sorry, how tall they are, in inches and feet, what their age is, and what the blood type is. So when this code iterates through, it prints out like Benito is 60 inches tall, 5 feet tall. Wait, okay, sorry. Benito is 5 inches tall, which is. Oh, sorry. sorry, is 60 inches tall, 5 feet, and it has who is 12 years old and has a blood type of A positive. And then, Caden's 3 feet tall. Alright, a good one is Caden is 3 feet tall. Yeah, that's it. That's actually not my blood type, so please don't hurt me. To find out, it's okay, guys. You won't. If I actually don't know what my blood type is. I should probably, but it could be a positive actually. But yeah, in terms of types of arrays, int double, fair string, unsigned long, dark. You guys know. Did Swabber go over darks? No. Oh, we had projects. That's a throwback to me.
Oh yeah.
We had a dark project. It's just a class. It's a class.
Wait, this was at Product 7.
Huh?
Product 7, the last one. Yeah, CS31.
Yeah, it would be a darks.
Yeah.
And then intervaling, like I said before, so for loops. Any loop iteration, you can also use pointers if you so wish. Alright. Okay. And now we're into functions. So functions kind of look similar to arrays except for now with parentheses, right? So you have a return type, you have your name, and then parameters which you want to put into your function that are exterior to the function itself. You can declare a function in any iteration. You put any parameters you wish. You just have to make sure you include the libraries that will work with it. Again, if you don't include the string library, or we won't know what string it is. So you have to kind of tell it what it is, and it's like, oh yeah, I can recognize that. It's really good for organizing code. Some of you might have used it for Arduino, just because the program is song just as a function. Like you could do void 90210 by Travis Scott, and then like it would run Travis Scott's 90210 track. Stuff like that. Void in terms of Arduino is, you know what that is in C++ too. It just doesn't return anything. It's a non-return type. While in terms of the functionality, if I do an int, it's going to return an integer. If I do a double, it's going to return a double. Those types of perspectives on it. It's also important to know that void setup is specific to Arduino. It's a built-in function. Void setup runs forever. It's important. I want you guys to know that for sure because void setup runs once. Beginning of your code, that's where you set all your declarations, right? And that's where Arduino reads it, runs it once, and then for the rest of its life, while it's connected to power, it's going to run the void loop over and over and over again. again, functions really simplify your life, like a lot. You can even put them in an H file on the side, and now you can have them in your main code block, so that way you just don't have to look at the gross stuff. You know? I really like that for when I did Arduino. I just had an H file on the side. I threw in all the songs, especially since they're void, and I didn't really have to write to any ends for that. I just had the play functions. Then I just implemented that as I'm including it into my C++, well, my C file and Arduino IDE, and then Nygren as well. It's kind of, wait, so actually that brings me up to a topic. So including an H file in Arduino, I believe the command is, if you're on Mac, it's Command Shift N or Command Shift H. Google it, but it's really simple. It's probably Control for Windows devices, Control H, Control N. All you have to do is that, and then it will pop up. It'll say like name your H file, and then you just name it .h. Boom, that's good for you. It doesn't have to be a header file. You can use CPP too. That's might be ahead. If you don't know a base knowledge of C++ and like C31 or C32, you don't really have to pay attention to that. That's just for people that you want to like look nice. That's optional. All right. So we actually have some example functions here too. So one of the functions, well, we use a function to get variables and we use that to calculate with those variables. We also have, again, types of functions like guards and other thing that you create a game. You know, obviously the name doesn't really matter, it's up to you. I highly recommend naming it something that makes sense. It's funny to have a meme name, you know, but there comes a point when you have like 17 functions and you don't remember which one sus1 versus sus2 is. I don't know what I've been looking at. So I highly recommend, if you're using multiple functions, to label them to a degree that you'll know. But maybe you just have like a list on this side, like, oh yeah, smallberg is this function, and Naschenberg is this function. And I know what that means. So basically these functions just run, so that one runs a product, it's an integer product, versus a double product. So it's important to note the difference between the two. If I have, like, let's say 1 times 2, that are the product function, it's going to return 2, right? But if I have 1.1 times 2, it's going to return 2 in the integer product as well. Okay, that's because it rounds down. It rounds to the extension. In terms of the double, it's going to run the actual. So if I run it with 1.1 times 2, it's going to return 2.2, which is the value we want for our hash, right? But doubles also take up more space in your Arduino, okay? They take more bit length because you have to account for, obviously, host decimal values. It also, there's also unsigned long. I don't know if we really like got in depth into that. Well, I think we did once, but you might not have used it yet. That's just a very long number. Unsigned means that it doesn't really matter the sign, right? It's 2's complement is still applied when it's back in the.
I don't know what two's complement, but unsigned just like uses, instead of the sign being a bit, it just have that bit. Like quantity of the number.
Yeah. So and then in terms of remainder double, those are just all functions for examples. If you guys want or have any questions about it, they're just basic division, multiplication, different data types. A lot of the common issues that we've gotten before are the fact that someone's trying to get the double value from integer operations. Okay? Another common issue is dividing between data types. So, or like doing an operation between data types. If you're using a built-in function for Arduino, and the function specifically calls for like 2 ints, but you don't really pay attention to using doubles, you might get an error there. So these are all things to pay attention to, especially when you're iterating through a lot of code. Nygren, like we said, is a lot more code than normal. So it's important to note that those errors might arise, and they might be. That I would recommend searching for those logical errors first, because those are going to be the hardest ones to find, but they're also like the most crucial. I was telling Miriam and Adrian earlier that like in my CS32 project 3, we did Battleship, and I was in the IEEE lab with Crane for like 3 hours trying to figure out what my bug was, because every 10 iterations of that project, I ran a Stack Overflow error. just out of nowhere. And I don't know if you know a lot about Smallberg, but Smallberg always tests like the edge cases. I was so afraid that Smallberg would just grade me F on the project because of that. So I spent like 2 hours in that lab, well 3 hours, but 2 hours trying to figure it out, and then Prim and I realized that I had a +1 somewhere, like deep down in a function that just completely exited the scope of the loop and then just ran forever. So because of that, like, logical errors are going to be an open source problems. Even if you think your code's going to run 100% the first time, it's probably not. And you just have to get used to that. Unless you're like so insanely cracked already at coding, and you might be. You'll probably run into an error or two. So just get ready for that. And,
Develop iterative.
Yeah, develop iterative. So start. Also, it wouldn't be a bad idea to start with pseudocode. We give you pseudocode in the project spec for Game Reno, but in terms on your own, please write pseudocode first and then start blocking from top down. Save you a lot of time, a lot of energy, a lot of compilation errors, a lot of logic errors too. So, all right. So now I'm going to go over a brief overview of Game Reno, but then I'm going to actually go through the spec with you guys too. We're going to do that, right? So in terms of the overview of the game, so it's the hardware portion is basically using OLED, which I'll talk about in a second, and a joystick with your Arduino. Those are the only two hardware pieces you're using for this. The rest is just code. The premise for the checkoff is coding tic-tac-toe. You'll have a fully working, functioning game of tic-tac-toe at the end of this project that you'll get to use with the joystick and the display on the OLED, or organic light emitting diode. That's the name. And yeah. Nice.
If you came to the project info session at the beginning of the year, this was...
Yeah, we had this up. So. Also, we'll be using joysticks. So the way joysticks work in terms of hardware is it's like two potentiometers, so to speak. They run the X and Y, like yin and yang direction. I think those are the other terms for it. There's also a switch, which is a button. If you press down the joystick, it'll act like a switch, like a button for you. They have 5 total pins, so you have your ground, your 5-volt input. You have your VRX, your VRY, your switch. The V on those stands for the voltage. Obviously, it's a potentiometer. What do you know about potentiometers? It's like a voltage divider on steroids. You get to change that resistance. So, in terms of that, that's why there's the V there. And X and Y is just direction. And switch refers to the light inside the joystick. Does anyone have any questions on the joystick implementation? At least with how that joystick works? You'll need to figure out, you'll find out pretty quickly when you run the project at first. We give you a recommendation to connect the joystick to your serial monitor and just see what it does by moving it around. So I highly recommend doing that before, so you kind of get a hint of what you're going to read normally. Yeah, okay. And then also, some basic logistics. So there's 2 main types of screens that you'll see. There's LCDs and OLEDs, which is liquid crystal display versus organic light emitting diode. For this project, we're using an organic light emitting diode because it's thin, it's really efficient. It can display a lot more colors on the spectrum, and it also uses carbon as an emitter. So also, I think it's more beneficial to the environment, which is nice because sustainability is cool. Especially if you guys are outside, it's snowing this week. Like here, at UCLA. Like I saw snow. Did you see that?
No.
No, it was weird.
Man,
I have a video of it. Like there was a small flurry. It snowed in Hollywood too, but yeah. So anyway, sustainability is cool. Also, liquid crystal display. So that's the cheapest option. OLEDs are much more expensive. I think by a factor of ×3 compared. But if you're buying a lot, it kind of adds up. They're also long lasting. OLEDs have this little issue of they can break pretty easily if you're not careful. So also, the way the LCD works is it shoots out light, and then there's a polarizer film on the other side. If you scrape off the polarizer, it would just be like white light. But if you have the polarizer on, it can identify the colors based on the chemical structure of the batteries. I remember kind of learning about that. I don't really remember much. Yeah. So in terms of those types of displays, you'll in your Arduino kit, you'll see the LCD. We're not using the OLED for this project, and you'll have to come to the lab to pick one up. But we have a lot. We have plenty for you guys. So, and they're also much cooler. They have like way smaller bits that you can work with versus that, which is like a little bit chunkier. And this is way like it's tinier, but it has a lot more capability. Like, and the resolution I would say is better too.
Yeah,
so.
absolutely.
For using our OLED, it actually uses I2C communication, which conveniently we just talked about. It uses only your SDA and your SCL. It has 4 bits of ground, VCC, SCU, and SCL. In terms of pinout, you'll connect your SCL to a PWM for clocking, and then your SDA. Oh, actually, yeah. Wait, no, SCL to A5. Yeah. And then your SDA, obviously, to where you're going to send your data to. In terms of the I2C actual stuff, we have built-in libraries for this because Arduino is open source. You're not going to have to learn how to actually like write from bare code I2C protocol. That's on the scope of ops.
The great thing about using, one of the main communication protocols is that usually somebody's already implemented it for you. So you can just, copy paste, put in that header file, and all of a sudden, hey, great, fantastic, I can use this easy.
Exactly.
So
We have
basically you build a whole
All right. Okay. And now, Game Guido. So actually, I'm gonna go. Do you guys want me to go through the spec again? Yeah. This is good. Okay.
Let me drag it over for you.
Sweet. In terms of any questions, do you have any questions about like from here on out? Our next project. Well, I'm kind of getting on this. Our next project doesn't really do too much with code. Well, kind of, but not really. It's interesting. We'll see. And then there's hash stuff. This project is super fun. It's definitely one of my most favorite projects, aside from the capstone itself, as the ops. Other than that, it's not really hardware implementation. I just liked it because like I could actually like play Tic-Tac-Toe on it. That was cool to me. But other than that, okay, ready?
Yeah, just the crane connect.
Okay, so wait, how do I scroll? Arrow?
Just like 2 letters.
Oh, okay. Okay, so well, I didn't know if the cursor was on this screen or like this screen.
Oh no, it's not.
Okay.
I changed it.
All right. No, it's fine. Okay, so Project 5 is Game Bueno. The due date is going to be Wednesday, April 4th at 5:59 p.m. You have a month to do it, and you have over break to do it. It's a hard deadline. We will not be giving out extensions for this project because we are giving you so long to do it. However, you guys have plenty of time. We're also hosting 2 work sessions, one next week, one the week after. If you guys want to get started early, just kind of get a feel for what it is. It looks scary. The spec might look scary, but we walk you through a lot of it. And then the little bit that I would say is like the do it your own, we kind of throw you into like figuring out how to operate the actual XO and tracking that and finding out like, oh, like, is this a match? Like, is this a tic-tac-toe or is it a cat? Stuff like that. Yeah, it's called a cat. We have the lecture 7 slides listed here. You will need to come to the lab and pick up your OLED and a joystick. We have those prepped for you. Obviously, if Miriam or I are not there, just ask another officer. Most officers know where it is. If they don't, then ask another officer. But they should all know where everything is. If they don't, they're trolling. They're trolling. So yeah. Otherwise, you'll just need a breadboard, your jumpers, and your Arduino for this one. We also say the 5-pin L-shaped header You can opt to use that or not. Because you have female to male wires in your Arduino kit, I would recommend those more, in my opinion, just because you can connect it to directly to the joystick. Because the headers that come out of the joystick are kind of horizontal. So otherwise, if you stick it in your breadboard, it's like vertical. It's kind of gross. So that's why we have the L-shaped header, so you can make it horizontal. I would recommend though using female to male wires, so that way you could just connect it to your breadboard, and you can have it like free roaming. So it can be more like a Joy-Con, like you use on your Wii, like a nunchuck. Yeah. If you still want it. All right. It's called Game Bueno, by the way. The B stands for Game Boy. We get that a question a lot. They're like, why is it not Game Bueno? Because that's not cool. It's called Game Bueno. Alright, so the first part about this is going to be designing your Game Bueno. For this part, we'll start with wiring. We walk you through the schematic here, and we tell you like the basics in this table. The schematics right here. The joystick, the OLED, and the Arduino. That's pretty self-explanatory. Just wire it like you would normally. If for some reason something doesn't work out, please recognize that you should use. Oh, okay. So, if let's say this probably won't happen, but let's say for some reason my SDA pin on my Arduino like shorted or didn't work, right? Arduino has two sets of these pins. I actually don't know off the top of my head what the other pair is, but there is another pair of SDA SCL that you can use. Just look at the panel for that, if so need be. Probably won't need be, but just in case, always refer to the pin out. This is correct though, so you don't have to worry about that. And then also, yeah. All right. If before you have questions, the VCC just stands for like power. We don't have it actually the wire connected directly to each of them with junctions. It's just connected to a bus. Miriam referenced that word earlier in terms of like for I2C, we kind of bus the values. That just means we take a bunch of wires, make them one. So for VCC, you connect that to your positive bus, which is your positive rail on your breadboard. The same for ground, and then you just connect everything there. Or if you know what ground is, you just connect it there. A good term to know also would be net. This is completely aside from the project, but net is also a common term. Net just refers to wires with similar nodes. Okay. All right, so tips, we have a tip section here too, and then we also have section 2, which is your joystick. So here we give you pseudocode to get you started. This is meant for analysis. This is meant for you guys to understand what your joystick is doing, how it's doing it, and what is going on. This is number one way of finding out what something does is just by serial printing it, especially if you're using Arduino. Just connect the device to it and then like mess around with it. We also have you do this so that you can understand calibration for this. It's good to know what your joystick's 0 is at, because Laura's 0 is not going to be the same as Ethan's 0 on their joystick. Okay. And then also we tell you about the dead zone here. It just walks you through that. I'm going to go a little bit faster. Section 3 is the OLED. So this is actually just connecting and managing the library. So we walk you through basically downloading the library that's essential for I2C communication. That's so that you don't have to manually do that. If you want, I would actually recommend like looking at the like the include file online if you want to. It's a lot.
I mean, they have to go into it.
Oh yeah.
The test.
Oh.
They have to go into the file and then they have to like switch.
No, they can just go to examples, right?
You go to the examples, and then within the examples, you have to change a couple parameters because like you have like knockoff stuff. So you have to like
Oh yeah.
give them a couple numbers and then it starts working.
Yeah.
Yeah, there's like a ton of stuff in there. It's pretty interesting.
Yeah, but yeah, it's a lot. So, oh yeah. Okay, yeah. Other than that, that's just a setup. By the end, you'll have this cute little GIF showing. It just calibrates the screen. Well, doesn't it? If your screen doesn't display something like this, and your code is 100% working right, and you believe it 100% is, please talk to me, Mirai, because it might be an OLED problem and not a U problem. like we said, it can get screwed up pretty easily. So just be on the lookout, okay? And then part 2 is software. So that section is all about graphics. We have you download this GitHub library from our previous lead, Preston. He was the one him and Margot made this project from scratch. That was their contribution. And then just download the libraries. That's a class structure. If you know anything about classes, that's what identifies the X's and your O's. It has the grid set up for you. Your main implementation of the code is going to be figuring out how to identify any tic-tac-toes and how to put an X and an O in a specific location. That's going to be your job, okay? We walk you through controller. Any Rihanna fans out there? No? Wow. Y'all been watching the Super Bowl? I watched the Super Bowl just for Riri, so. Other than that, we walk you through, we tell you basically what to do. But again, this is more of a you thing. From now on, we aren't really going to hold your hand when it comes to projects and stuff. Obviously, come to us with help and questions.
Go to work sessions.
And go to work sessions if you want your handheld. It's totally fine if you do. But in terms of the specs, they're going to get a little bit more ambiguous, and that's not because of us not wanting to give you it, but because we want to see where your intuition lies and what you do with it. Because if you want your screen to light up when someone wins, you can do that. That's up to you. It'd be cool to see your own intuition in this, and especially in the career, we want to give you much more things to speak of on your resume. Some you might do this project, but then you want to push yourself forward and make something cooler. That's definitely up to you. All right, and then after that, we have victory. So that's obviously identifying your win, being able to identify what a win is. You can do that in a variety of ways. Some people use 3-dimensional arrays. Some people use 1-dimensional arrays of 9 of the item type they're using. It can be a char, it can be int. It's up to you again. The code is all up to you. And in terms of checkoff, you will have to submit the full game to the checkoff form. Full game of tic-tac-toe. You can play with a friend, you can play by yourself, whatever. Actually, I think we might edit that to show a loss and a win. Do you want to do that? Well, no, like oh yeah, that's true. Oh yeah, never mind. Other than that, you submit your project to the link. Remember, it's our deadline. That's just like, if we're giving you this much time, that's okay. Also, I don't want you guys to fall behind with like Gameduino, like a project, like the capstone. But we don't want those to overlap, And project 6 doesn't take too much time. So it's literally like project 6 and then capstone for the rest of the board. So we don't want those to overlap because both are pretty big, hefty projects, okay? And in terms of part 3, this is the final part. It's a competition. It's up to you to decide what you want to do with the competition. Again, it's your game. It's your game, Guido. You can design any game you want in it. In fact, you could just make a better tic-tac-toe if you wanted to. It's all up for fair grabs. There's going to be a good prize, like a really good prize. We're talking with the treasurer right now about using funds from the ops budget, like actually, to implement some nice software. And then also, well, not software, sorry, gifts. Sorry. Also, just in general, have fun with it. Someone last year coded Tetris, which was really cool. So, and I think someone coded Tetris. You do not need to code Tetris. Yeah.
So any kind of creativity is very much appreciated.
Yeah. And then we are trying to get something cool aside from prizes there. Project Ice Spice. It's gonna be dope if it happens. If it doesn't, I don't want to keep your hopes up. But otherwise, I think it'll happen. I think it'll happen. Yeah, because it's cool. Also, it's a funny project game. Anyway, other than that, that's it. We also have some tips on how to make it your own Game Bueno. It doesn't just have to be coding. You can implement more hardware into your regular tic-tac-toe. Once you get it working, you could just implement like LEDs, like it lights up, it does like a cute little like RGB thing. Yeah, like stuff like that. You could reuse stuff, you know, or you can decide to and opt to make actual like more sufficient game other than TikTok's. That's all up to you. So that's the base of the spec. We're actually gonna end the sandwiches now. So thanks for coming, guys. And then yeah, that's it for ops lecture. So sweet.
We end the recording. Recording. Figure it out.